Good morning, students. Myself, Satish Kumar. In this video lecture, I'm going to present the array factor for the linear array with n isotropic point sources, which are excited with currents of equal amplitude and equal spacing. I told you already the same thing in the last lecture that once we complete the radiation pattern analysis of two-element array, we need to extend directly it for n-element array, because when you get an array factor for n-element array, we can substitute n equal to 3 to get the radiation pattern of three-element array, and we substitute n equal to 4 to get the radiation pattern of four-element array, like that, so on. We can extend it for n-element arrays also. Okay, that's what we are going to see in this video lecture. Here we are going to find out the array factor, which is nothing but the normalized field component of the n-element isotropic uniform linear array. Okay, so let's see that in this lecture. Right. So if you look at this particular diagram, we have n number of isotropic point sources: 1, 2, 3, 4, 5, so on up to n, and each and every element, adjacent elements, are separated by a distance d. Okay, so let us of course we express that distance d in terms of wavelength later, but we will be now considering that distance or separation between any two adjacent antenna arrays is d. And we are going to find out the maximum or total electric field intensity at a far distant point P, okay, of individual n element arrays, n element array. Okay, and the field expressions, okay, this is E1, which is equal to E naught. Of course, we can also call this is e power j0. Okay, and this is E2 because it is for second antenna, and so on. This is En. Okay, En equal to this. Okay, if you observe this carefully, for E1, okay, this is e power j0, that is 1 minus 1, less than 1. E2, it is j1 psi, and this is E3, which is e power j2. That means whenever 3 is here, we are getting 1 lesser than that. Whenever we have n is here, n minus 1 psi will be the electric field. And these total electric fields we have to add at this far distant point. Even though these are mentioned here, these are the values which we will be getting at this far distant point. Okay, so to get the total electric field intensity, and from that we will find out the normalized field component. Okay, we will be adding all those. Okay, but before that we will try to see the analysis of this first. Okay, so first let us assume this particular array is a linear array. Let the above array is a linear array. Okay, what do you mean by linear array? It is array is said to be linear array if the separation between any two adjacent element is d, and which is same for all the cases. That means the separation between the two elements in an antenna array will always be same for all the n number of elements. Okay, that's what is called linear array, and it is also uniform linear array. Okay, the uniform linear array means all the elements are equally spaced and they are excited with currents of equal amplitude and equal phase. How can you say equal phase? Okay, so we already know that from the 2-point arrays, the phase difference between any two adjacent antenna elements is psi. Okay, so this is j psi minus it is e power 0. Psi minus 0 is psi, and this is 2 psi minus psi, it is 1 psi. 3 psi minus 2 psi, 4 psi minus 3 psi. Everywhere the phase difference between any two adjacent element is psi, which we have already derived for the case of two-element array. The same thing is valid for n-element array also. First of all, why do we go for n-element array? What is the problem with two-element array? Okay, so the reason for going for n-element array is in point-to-point communication, we require the communication or the transmission of the signal must be from one antenna to another antenna, because this antenna will be transmitting and there is another antenna which is kept at one distance. Okay, let's say this is one antenna and this is the place of the receiving antenna. Whatever is the signal that is being transmitted, it has to go in a single direction. That means the radiation pattern must be like a pencil beam radiation pattern. That means it should be very sharp. Okay, to get this much sharper radiation pattern, okay, whose half power beam width and Fresnel beam widths are very smaller, maybe less than 2 degrees, 3 degrees. Okay, so in that particular case, this cannot be achieved by using a single antenna or two antennas. We have to go for n number of elements. That means we have to go for n element array. Then only we will be getting this kind of sharp radiation pattern. But in some cases, what will happen is, as the number of elements increases, there will be some side lobes also that you will be seeing after we complete the array factor. And while seeing the broadside array case and end-fire array case for 4 element and 8 element, you will be seeing the side lobes. But how do we minimize those side lobes and all? We will be seeing in the further classes, right? So that is the basic idea of going to an element array. Okay, so now let us try to find out the total electric field intensity first. Okay, so it's very clear from the diagram that E1, which is due to the antenna 1, which is equal to E1, as we know very well that it is E naught into E power J0. It is not E power J0 1, right? And E2 is equal to E naught. Why in both the cases it is E naught? Because they are excited with currents of equal amplitude. When they are excited with currents of equal amplitude, as the antennas are similar, then you will also getting the field amplitudes are also same. And phase difference is psi. That means they are excited with equal phase also. This is nothing but actually the broadside case. Okay, so now E2 equal to E naught into E power J psi, and E3, which is equal to E naught into E power J2 psi, so on. And what we'll be getting for the case of En is, it is E naught into E power J n minus 1 into psi, E power J n minus 1 into psi. So to get the array factor, what we have to do is we need to get the total electric field intensity. Okay, the total field at the far distant point. Total field at the far distant point P is, okay, so let us denote that with ET, okay, which is equal to E1 plus E2 plus E3 plus so on En. Okay, don't represent this as 1. After substituting the values, we'll try to represent it as 1. Et will be equal to, it is E naught E power J0, that is anyway 1, plus E naught into E power J psi plus E naught into E power J2 psi plus so on. En is E power J into n minus 1 into psi. Okay, and what is common in this is E naught. Let us try to take that as common and represent that equation as first equation, right? So it is 1 plus E power J psi plus E power J2 psi plus so on E power J n minus 1 into psi. Okay, call this is equation number 1. Right, now to get the array factor, this is not just enough, because you cannot get any expression for this entire one in terms of either sine or cos. Okay, converting this kind of bigger expression into trigonometric form is not possible. For that, what we do is multiply the equation 1 with e power j psi. Okay, I'll just tell you what happens if you multiply the entire expression, equation number 1 with e power j phi. But let us try to do that. Multiply equation 1 with e power j psi, with e power j psi. Okay, so this is et into e power j psi is equal to e naught, you keep it as it is, and 1 into e power j psi is e power j psi, plus e power j psi into e power j psi is e power j2 psi, plus e power j2 psi into e power j psi is e power j3 psi. That means here if it is 2, it will be increasing by one value. This n minus 1 will become n, that is e power jn psi. Call this is equation number 2. Okay, so now let us try to take 1 minus 2. 1 minus 2. Okay, what will happen if we do 1 minus 2? Observe carefully. On the left hand side, what we have is et, and this side et into e power j psi. Let us take et common. Okay, et into 1 minus e power j psi. What will be getting cancelled if you subtract 2 from 1? If you subtract 2 from 1, then what you will be getting is this e naught into 1 will be there as it is, and e naught into e power j psi, and this is e naught into e power j psi, first term. In this equation, second term, in this the first term will be getting cancelled. In this third term, this second term, fourth term and third term, and this term and before this term, okay, will be getting cancelled, and what is remained is only this e naught into 1 and this e naught into this e power jn psi will be the terms which are remained. Okay, we'll be trying to draw that. So write that e naught into 1 minus, it is e naught into e power jn psi. Okay, this is what is left. Okay, we will be trying to take out e naught common in this also. So this is e naught into 1 minus e power jn psi. Jn psi. Okay, this is now et into 1 minus e power j psi. Okay, but I want et, therefore what you get for et will be equal to e naught, you write here as it is, 1 minus e power j n psi by 1 minus e power j psi. Okay, this is what is the expression. It's not over yet. Okay, don't think that it is completed. You have to convert it in the form of trigonometrical functions, right? So how do you convert this into trigonometrical functions? Anything exponential e power j theta can be written as e power j theta by 2 into e power j theta by 2. Is it possible or not? Because a power m into a power n is a power m plus n. When you take e power j theta by 2 into e power j theta by 2, it is e power j into theta by 2 plus theta by 2 is theta. Both are same. Do the same thing here in the numerator as well as denominator. Then et will be equal to e naught into, what you do is 1 minus, write this or split this j n psi by 2 into e power j n psi by 2 by 1 minus e power j psi by 2 into e power j psi by 2. Okay, so this is how we split this numerator and denominator, and what you now do is you take out this term common as well as this term common, right? So what you will be getting is et will be equal to e naught, you take as it is out and take this term common. So e power j n psi by 2, you take it common, and in the denominator you take e power j psi by 2 if you take it common. What you will be getting is, because here it is 1, so e power j n psi by 2 into e power minus j n psi by 2, because Here actually you should write 1 by e power j n psi by 2. That 1 by e power j n psi by 2 is e power minus j n psi by 2 minus what is there is e power j n psi by 2 by the same thing here also e power minus j n psi, sorry, j psi by 2 minus e power j psi by 2. That's it. Okay, this is your expression. Once you get this, you will be now writing this in terms of sine. Okay, because sine theta will be expressed as e power j theta minus e power minus j theta by 2j, but here there is no 2j. Okay, just arrange 2j and 2j for both numerator and denominator. Then what you will be getting here is et is equal to e naught into, bring this term to the numerator, what you will be getting is e power j into n minus 1 by 2 into psi. Okay, yes, this is right. And by 2j you arrange. Okay, then and take out minus common, because e power j theta minus e power minus j theta. If you take minus common, if you get here, minus here, plus here, minus here. I am multiplying both numerator and denominator with minus, you will be getting this. Now it is exactly like sine n psi by 2 by sine psi by 2. Okay, sine n psi by 2 by sine psi by 2. And this n minus 1 by 2 into n minus 1 by 2 into psi can be called as some 5. It's just a phase angle. Whatever is the number of elements here, minus 1 by 2 into that psi will be denoted by another angle. So finally, what you will be getting is Et is equal to E naught into e power j phi into sine n psi by 2 by sine psi by 2. Okay, so this is your expression, but still it is not your final expression. We will further need to be simplified this. Okay, simplify this. Okay, so this is e power j phi. If you take the magnitude of et or shift this entire array with respective to origin, okay, this e power j psi will become 1, or else you take magnitude of et, okay, then magnitude of e power j omega will be 1, all the remaining components will be present as it is. That means e power j theta will become 1, then your expression will be sine n psi by 2 by sine psi by 2. Okay, but this is only the mac total, e total electric field intensity, but you need E normalized component, that is called array factor, that is ET by ET maximum. But how do you get ET maximum? Okay, if you have only sine function in the numerator, you can take that, but here both numerator and denominator you will be having it. Okay, so if you try to take psi equal to 0 here, then you can able to get et which is having a maximum. But when you take psi equal to 0, then sine 0 by sine 0, 0 by 0, that is in indeterminate form. Whenever you will be getting it in indeterminate form, you have to go for L'Hospital rule. Okay, so everybody might have remembered what is L'Hospital rule. Let limit psi is tending to 0, then et will be giving you et maximum. Same thing, limit psi is tending to 0, e naught into sine n psi by 2 by, this is, okay, this is only sine n psi by 2 by sine psi by 2, right? Okay, so once you substitute this psi is tending to 0, this will become 0 by 0, that is in indeterminate form. Indeterminate form. So then you have to go for L'Hospital rule. Okay, everybody is familiar with what is L'Hospital rule. You have to differentiate this numerator with respect to psi as well as denominator with respect to psi, and this will become limit psi is tending to 0, et will be called as et maximum. You will get the maximum value of that particular et, and then limit psi is tending to 0 will be there as it is, e naught will be there as it is. This is d by d psi of sine n psi by 2 by d by d psi of sine psi by 2. Okay, what you will be getting now is this E naught, you take it out, E naught you take out of that limit, and limit psi is tending to 0, d by d psi of sine psi by 2 is sine will become cos n psi by 2 into, again differentiate that n psi by 2 with respective psi, you will be getting n by 2 by d by d psi of sine psi by 2 is cos psi by 2, and again d by d psi of psi by 2 is 1 by 2. What will happen here is will be getting cancelled. Sine, when psi is equal to 0 tending to 0, cos psi, cos n psi will be cos 0 by cos 0, that will become 1 by 1, that is e naught into what is left is only en, which is your et max. So once you get et max, you can able to get E normalized component. Okay, I gave you the expression for E normalized component is this, that is Et by Et max. Et is this, that is E naught into sine n psi by 2 by sine psi by 2, and Et max is E naught into n. Just substitute that in the expression for E normalized component. The expression once again I am writing Et by Et max, okay, which is equal to, what you have got is E naught into sine n psi by 2 by sine psi by 2, right, by E naught into n. Okay, this is what is Et max. E naught getting cancelled, and your final expression for E normalized component, or this is also called array factor. Very important question in engineering. Okay, is equal to 1 by n into sine n psi by 2 by sine psi by 2. Okay, so this is the expression for array factor for an element array. So once you get this array factor, you can able to get the analysis of n element broadside array as well as n element end fire array. Okay, we will see the complete analysis of n element broadside array and n element end fire array by using this array factor of n element array. Okay, so hope you like this lecture. In case if you like, okay, please subscribe my channel. You will be getting the entire antenna and wave propagation lectures in my channel. Thank you very much.